And then the reducible hyperkähler condition means that I have a holomorphic symplectic form. So I have some, if I have the space of holomorphic 2 forms on X should be generated by a single form sigma. And this sigma is a symplectic form. So sigma is non-degenerate. Which means that if I take the map from the tangent bundle to the sheaf of 1 forms by contraction with sigma, that should be an isomorphism. OK? So the irreducible part means that this is really just a one-dimensional space, right? So the general theory is that this space here could have dimension more than 1, in which case X would split up as a product of irreducible pieces. OK, so the kind of examples of this would be if you have a K3 surface, that's the smallest sort of example, then you can take Hilbert schemes of K3 surfaces, for example. And in general, there's very few known examples of these things. So all the known examples are sort of constructed either from K3 surfaces as moduli spaces or from abelian surfaces. I also wanted to say that, so I'm assuming it's compact Kähler, but the story is just like for K3 surfaces. So these things, they have some moduli spaces, and the general point in the moduli space is just compact Kähler, but there's a dense open set where things are projective, just like for K3s. So it's, if you like, you can assume it's projective. OK. It is quite possible that at the end of the day, maybe if people at some point manage to classify these, maybe they'll be they'll all come from surfaces in some way, maybe. But so this is sort of working in this area is maybe a bit of a game because you might be proving theorems about very restricted classes of things, but who knows? It's still fun to work on prove general results. OK. So one general result concerns maps here. OK. So before I get to Hwang's theorem, I remind you of Matsushita's theorem. So Matsushita showed that these things admit very few maps, only very special maps. So say f from x to b is a fibration. So surjective connected fibers. And then if the dimension of b, oh, I should say here, so the dimension of this thing is always even, and I'll always call it 2 times n. And so if the dimension of b is not 0 or 2n, then f is Lagrangian. A Lagrangian fibration. And so what this means is that, so if x sub b is a smooth fiber, then sigma restricted to the smooth fibers is trivial. And also, they have maximal dimension. So the dimension of the fibers is n. OK, so the fibers are Lagrangian submanifolds. And then this, of course, implies that the dimension of b is equal to n. OK, so the only sorts of maps you can have is you map to a point. Then you can have maps among different compact hyperkähler things of the same dimension. But every other non-trivial map is a Lagrangian fibration like this. OK. And so the goal is to understand these fibrations because, again, if you wanted to some extent, classify these things or understand their structure, these are basically the only maps that you can work with. And then there's all kinds of basic results about these Lagrangian fibrations. Again, they mostly come from work by Matsushita in a series of papers. So there's some sort of general facts. So in this sort of case, the base B, well, it's always, I mean, sort of by definition, it's normal, but it has at worst KLT singularities. It's Fano in the singular sense. Is simply connected. The Picard number is 1. And in fact, the singular cohomology of B is the same as the cohomology of projective space of dimension n. Okay? So in very many ways, this B looks just like projective space. Yeah, and so, right. So I think then Matsushita himself raised the question of whether B is actually projective space. And so this theorem by Hwang is about that problem, right? So the main theorem is this one, that if B is smooth, so if f from x to b is a Lagrangian fibration, x is irreducible hyperscalar, and if B is smooth, then B is Pn. Right? That's the result. Oh, yeah. No, right, he told me, but they don't break if I move them manually, do they? Well, okay. I mean, I can use the buttons if you like, but okay. So that's the statement, right? The irreducibility is needed because otherwise you can get things like products of projective spaces, right? So for instance, if I took S to be an elliptic K3, that's an example of a Lagrangian fibration. Then you can do things like S cross S mapping to P1 cross P1, right? So in this case, this thing is not irreducible because there's two independent two forms, and the base does not have to be P1. It will be P1 cross P1 in that case, right? But for example, if I take the Hilbert scheme of 2 points, then map to P2, and then it'll be the sort of irreducible Lagrangian fibration. Okay, and so my plan is basically I want to describe a somewhat simplified proof of this. So which is joined with Ben Bakker. Okay, so it's simplified in the following way that some of the steps of the proof are really just more or less the same thing that Hwang does in his paper, but we use a certain amount of more Hodge theory in order to make some other steps simpler. Okay? So I'm going to give you a kind of sketch of the proof of it, but where some steps are really quite sketchy. And then at the end, if I have time, I maybe talk about some of the Hodge theory that goes into it. Okay. So any questions? Or? Oh, okay. Yeah. I think integral cohomology would be difficult to compute for the base. No, I don't know. Okay, all right. So maybe let me start with a bit of again some general facts about these Lagrangian fibrations before I can sort of tell you the strategy of the proof. So so some more background. So again, F is always a Lagrangian fibration. Okay, so what else can one say about it? So the first thing, again, these things are mostly due to Matsushita, but so the first thing is, if you and we're going to assume that the base is smooth. The first point is that this Lagrangian fibration condition is a statement about the smooth fibers, that the smooth fibers are supposed to be n-dimensional and Lagrangian. But in fact, Matsushita showed that all the fibers have the same dimension n. So this F is actually equidimensional. even the singular fibers have dimension n. Right? And so then because the base is smooth, this implies that f is flat. The other geometric fact is that the smooth fibers, they have trivial canonical bundle and trivial tangent bundle. So they're the abelian varieties. So the smooth fibers are abelian varieties of dimension n. And so that you can see like this. So this I should explain anyway. So first of all, we have the discriminant of f. So where the fibers are singular, and this is a divisor always. So this I guess I'm going to call it D. Okay, so this is a divisor in B. I think this is a result by Hwang and Ugi. So. And so then if you look away from this divisor, then you have smooth fibers. And so away from D, you can do the following. So on B0, which is B minus D, then the Lagrangian fibration becomes smooth. So you have 0 to 0. And then you can draw the following diagram. So you have the tangent bundle of x0. And the tangent bundle of x0 is by the symplectic form isomorphic to the cotangent bundle of x0. And then you have the two sequences for the tangent and cotangent bundle. So for the cotangent bundle, I have the pullback of the forms from the base and the relative cotangent bundle. And for the tangent bundle, it goes the other way. Relative tangent bundle. And then the Lagrangian condition actually means that these two sequences become identified. And so those two vertical maps are also isomorphisms. Okay, so the tangent spaces to the fibers become identified with the pullbacks of the cotangent spaces at the base and the other way around. Okay, and so for example, you see from this isomorphism here, for example, you see that the tangent bundles of the fibers are trivial. So then the fibers are compact complex tori of dimension n. And then there's actually an argument with Kähler classes to show that they're actually projective. Okay? So this is why they're abelian varieties. And you also see from this that, so for example here, if I push things forward again, you see that the push forward of the relative one forms is isomorphic to the tangent bundle on the smooth part. Right? And the push forward of the relative tangent bundle would be isomorphic to the one forms on the smooth part. Okay, wait. Can you do two at the same time? Okay. All right. I don't think it's really any better. I mean, it takes longer and it can only do one.
Gives people time to absorb.
Yeah, okay. Okay, maybe. Okay. Yes, and then for the Hodge theory, the part that I also want is, so on B0, you get a variation of Hodge structure. That I'll call V by taking the H1. Well, okay, let's do it with Q. Taking H1 of the fibers, right? So this is the H1 of the fibers, and then has this decomposition into So these Hodge structures of rank 2n and weight 1 from the abelian varieties. And so this has an associated flat bundle that I'll call curly V. So V times the structure sheaf of the base. And then the interesting thing is that the Hodge bundle, so the bundle of 1, 0 spaces on the fibers, is actually the tangent bundle of the base, right? Because this is the F0 lower star of the relative 1 forms, and that's the tangent bundle of the base, right? So this is this will be the main object, this variation of Hodge structure. And again, you get geometric consequences about this space B out of it exactly because the tangent bundle shows up there. Okay, that's kind of the key point. Okay, and so then there's two other facts. So there's a result by Voisin that says that this V is irreducible as a VHS. Okay, so V doesn't split in any way. And then the second bit is another result by Matsushita. So this variation of Hodge structure here, this only exists on the complement of the divisor, right? It only exists on the part of the base where the fibers are smooth. But there is a certain amount of extension that you can do over the base, and so this kind of fact can be generalized. So what Matsushita says is that if I look at the higher direct images of the structure sheaf, which are the same things as the higher direct images of the canonical bundle of X, because the canonical bundle is trivial, then these are actually the sheaves of forms on the entire base, so on all of B. Okay, so this generalizes to some extent those facts. So here, when I'm doing the 1, 0 forms on the fibers, I get the tangent bundle of the base. And this is some statement that if I'm doing forms of type n, I on the fibers, then I get cotangent bundle of the base and so on. Okay, so these are the inputs. Okay, and so then the outline of the proof is like this, just to fit it on one board. So the way that we show that this thing is Pn goes like this. So if B is not Pn, then what happens is that you can find rational curves in the base of small degree. Okay, so I'm just giving a sort of one board outline of how the argument goes. So there is a characterization of Pn in terms of rational curves and degrees of rational curves. And by that characterization, if B is not Pn, you can find curves that have relatively small degree measured with respect to the anti-canonical class. And then we use a Hodge theory argument to show that this variation of Hodge structure, V restricted to such curves, has a fixed part. Okay, so when I restrict this V to one of these curves of small degree, it splits up into a trivial part and a non-trivial part. And then you can argue that because these curves, there's a lot of these curves, and they cover the space and so on, one can actually go from here by some complicated argument to showing that V has to split not just on each of these curves, but V has to split on all of B. So then V splits on on B0. And then, of course, that contradicts Voisin's theorem. Okay, so that's the logic of the argument. Yes. Yeah, that's right. So these curves of small degree, if I have one of these curves that meets B0, then I can restrict the VHS to the open part of that curve. And then it's a VHS on the curve minus a few points. And so there, that thing has a fixed part. That's how it, right. So, I mean, anyway, I'll say this in the more careful outline of the proof, but directly from the VHS, you only get information about the tangent bundle of B0, but there is a way to see the whole tangent bundle on all of B. Yeah, by some extension. So any other questions? Yes? Yeah, right. So this is actually, this is a result by Ben that, again, this was a conjecture by Matsushita, that if you look at the moduli of the abelian fibers, the thing is either isotrivial or they vary maximally in moduli, meaning that the map to moduli is generically finite, right? Yeah, so in fact, interestingly, so I mean, this project of trying to give a simplified proof, this got started exactly after this result, because it seemed like this dichotomy between either isotrivial or maximal variation should be useful in this thing. And in the end, it wasn't, but it's sort of, that's how we got started talking about it by email. There's another simplified proof of this where they use the dichotomy by Tosati and Lee. So they actually make use of it by some metric construction, and for the metric stuff, it helps to have this dichotomy. All right. Yeah, maybe I can also say that, so originally, when we started thinking about this, we thought that somehow the first step was the interesting, tricky one. So this, how to get information on individual curves. But it turns out that that's actually not the complicated step. So the complicated step is really some technical business about the end, at the end, how to go from one curve to what happens in general. But anyway, we'll get there. Okay, so I'll give a sort of less outliney part sketch of the proof in 4 steps. Okay, so step 1 is this business about recognizing Pn in terms of curves, right? So we look at rational curves. And so for me, I mean, if B is here, you know, the rational curve isn't necessarily smooth, but the rational curve for me is always some map from C, which is P1. Okay, so I'll always write my rational curves as a non-constant map. Where C is isomorphic to P1. I could call it P1, except somehow P1 is better when you've chosen coordinates. And then later, this curve C will vary in some moduli space, and so I don't want to call them all P1. Okay? And then you measure the degree of such curves. The degree is really the anti-canonical degree. Right? Because the base is Fano minus KB is an ample Q divisor. So you can use this to measure the degree. And so this is the same thing as the degree of the pullback of the tangent bundle on the curve. Okay, and then the way that you recognize Pn is it's basically Morris theorem about degrees of curves, except that in our case we don't want to talk about all curves in B, but we only want to talk about curves that meet this locus B0, because that's the locus where we have the nice Lagrangian fibration. So what we actually use is this following version of Morris theorem, which is due to Cho, Miyaoka, Shepard-Barron, and some little addition by Quebecus. So it says that if B is smooth and uni-ruled, so covered by rational curves, and if there is some open, some non-empty open B0 in B, such that every rational curve that meets B0 has degree at least n+1, n is the dimension of B. Then B is Pn. Okay, how you spot Pn. I think so. The kind of assumptions that you would get out of Morris' original paper would be if this was true for every rational curve. And so here the big technical advantage is that you only have to look at rational curves to a generic point, basically. So that, this is very well adapted to our situation. Right, and so then, in fact, the minimal degree that shows up is actually n+1. Right, because if a curve has degree at least n+2, so if you have degree n+2, then you have enough moduli to actually move the curve and keep 2 points fixed. And then you can run this bend and break argument where you look at a one-parameter family through 2 fixed points. And as that deforms, the curve will break. And once it breaks, the pieces have smaller degree. Right? So if the rational curve has degree n+2 or bigger, you have enough moduli to break the curve. And so the minimal degree is in fact n+1 in that case. And then, of course, the rational curves of minimal degree end up actually being the lines on Pn. And so these end up being the lines on Pn. Right, so you show that these curves of degree n+1 through a point, they behave exactly like the lines, and you can blow up and do some inductive argument to show that this thing is Pn. Okay, and so in our particular setting, as indicated by the notation, the open set will be the smooth locus of the Lagrangian fibration. And so what we need to show is, so for us, we need the degree of the tangent bundle to be at least n+1 whenever for rational curves that meet B0. That's the situation that we get into. Should be the other way around here. B is projective, yes. But you mean projective as opposed to compact Taylor, or projective as opposed to quasi-projective? B is projective because the pk number is 1. And in fact, minus kb is ample, right? So, I mean, it's actually Fano and so on. So, yeah. Right. I mean, I think everyone believes that B will always be Pn. So, no. OK, right. So this is the kind of thing that we have to show. And so now the second step is how do we actually control the degree, right? So control degree. So I can always, if I take one of these curves, C is P1, right? So if I pull back the tangent bundle, then because it's on P1, it's going to split up into a sum of line bundles like this. Right? And so the control of the degree comes from Hodge theory. So there's a small Hodge-theoretic argument that says that as long as the curve meets, so as long as the curve meets 0, you can show that these integers ai are all non-negative. Okay, so the pullback of the tangent bundle is semi-positive in that sense. So this, if I have time at the end, I'll sketch you the proof of this semi-positivity, how that's done. Okay, this is a not so complicated argument. And then the second part is, so it could happen that some of these AIs are equal to 0, in which case the pullback of the tangent bundle has some trivial part. And the trivial part is also understood Hodge-theoretically. So the maximal trivial summand in G upper star TB comes from the fixed part of the VHS. Right, so if I, again, maybe I'll write it like this. So this is the part of the curves that lives over B0. Then we know that the F1 is the tangent bundle of B0. So when I pull back, when I pull back the tangent bundle and then I restrict it to the part of the curve that maps into B0, then I'm really getting the F1 of that Hodge bundle. Sorry, the notation is kind of awkward, but okay. So the pullback of the curve, the pullback to the curve of the VHS knows about the pullback of the tangent bundle, at least over the smooth part. But the point is that if the tangent bundle, which exists on the entire curve, if the tangent bundle has a trivial summand, then the VHS actually has a trivial part, a part without monodromy. Okay, so this is the meaning of this part. So if there's some zeros here, then they have an explanation in terms of this variation of Hodge structure. And so the way that relates to this bounding the degree is as follows. So I always have the pullback of the tangent bundle. This always contains the tangent bundle of the curve, which is O of 2. And then I have the sort of normal bundle to the map, right, where this is the normal bundle, some sort of normal bundle. Right? So the degree of the tangent bundle is always at least 2. And one of these AIs is at least 2. And so then what happens is, if this thing is not Pn, so meaning if the degree of these curves is not n plus 1 or bigger, then it's less or equal to n. But then because one of these numbers is equal to at least 2, and all of them are non-negative, then if this is less or equal to n, then there has to be at least one 0, right? So now if the degree of the pullback of the tangent bundle is less or equal to n, then at least one AI has to equal 0. And so by 2, the VHS has a fixed part. And so this VC, which is the pullback of the VHS to the open part of the curve, has a fixed part. Okay, and so then in that case, I get this kind of decomposition into the fixed part and the part that's not fixed, where this is here the local system is trivial. Right, that's what ends up happening. So if B is not Pn by contradiction, then this has to happen, and so then I see it in the VHS by the VHS having a fixed point on each curve. Yeah. Well, because all of them are non-negative, and there's n of them, and one of them is 2 or bigger. Yeah, right. So the result of step 2, the thing that you have to prove, which is kind of 2 propositions or something, is these 2 statements, right? But I guess I'm following the principle that once I've written it on the board, I'm going to assume going forward that it's true. So yeah, right. So in particular, you have this. Yes. Okay, and then because the information that we have about V is irreducible on all of B0, then now we have to look at how we can go from what happens on each curve individually to what happens on the entire space B, right? And so for that, obviously, you have to move the rational curves, right? Okay, so now we deform. So in step 3 is we deform the curves. So I guess, so now numerically, so I'll assume that B is not Pn. So the minimal degree of rational curves that meet B0, I will call this I think k plus 2, and then k is between 0 and n minus 2, right? So the minimal degree of rational curves meeting B0, it will be less or equal to n, and it will be greater or equal to 2 because I always have this 2 there. So then the degree of G alpha star TB is k plus 2, and k is really the degree of the normal bundle. And then what we look at is, so let's call this M. So M will be the moduli space of rational curves of degree k plus 2 that intersect B0. Okay, that's our moduli space. So it doesn't really matter which one you use. I mean, if you like, you can use stable maps or something like that. But because we're only looking at curves that meet B0, they'll all be very nice. So in practice, I think we use this moduli space from Kollar's book on rational curves. So I think Kollar calls this like the rat curves N, like the normalized moduli space of rational curves or something like that. That's convenient for this thing. The main thing, if you're a moduli person, the main thing is that because we're only looking at curves that meet B0, we cannot arbitrarily degenerate. So this M is not going to be proper, right? So this is not proper. Okay, but still the situation is very, very nice with this moduli space because of the result from step 2. So let's maybe first write all this down. So this space of rational curves comes with a universal family. So we have the universal curve that I'll call C to M, maybe pi or something. Now, because we're looking at curves of minimal degree, all of these curves that intersect B0, they have to be irreducible, right? So they have to be P1s. So, this is really a P1 bundle, right? The curves that meet M0, the curves that meet B0, they can never break because we're already looking at the curves that have minimal degree. So they cannot be reducible. Okay, so I picture it like this, that here's this universal curve, which has fibers that are really P1s. I'll just call them C. I map down to that moduli space M, and then I have a kind of evaluation map over to B. So this G is the evaluation map. Okay, over here the curves are P1, but of course their images could look like this. They can have singularities and stuff. And the thing that's very nice is that the deformation theory that controls the moduli of these curves, that's all coming from the cohomology of the normal bundle. And in our case, we have this semi-positivity, and so that cohomology is trivial. And so that means that everything is smooth. Right? So in our setting, the deformation theory is controlled by H1 of the normal bundle, which vanishes in our case by the semi-positivity. And so what this gives us is that C is smooth, right? And we can compute the dimension. So the dimension of C is the H0 of the normal bundle. So that's the degree of the normal bundle plus the rank of the normal bundle. That's K plus n minus 1, I guess. Sorry, that's the dimension of the moduli space. I meant the moduli space. And then the dimension of the universal family is one bigger. Okay, so that's the normal bundle. And then the fact that actually the pullback of the tangent bundle also has no cohomology, that means that even this evaluation map G is a smooth morphism. So G is a smooth map. Okay, so everything is very, very nice from a moduli point of view. Okay, also, so these curves, because of that condition 1, they're what's called free curves, right? So if I take a generic curve in this moduli space, for example, it's known from general theory that it's immersed. You can have at worst nodal singularities, things like that. So everything's quite good. Okay. Yes, and so right now the starting point was that so if B is not Pn, then on each curve in this family we get this decomposition. And now we want to globalize the decomposition. And so what we can do is we can get a decomposition on the universal family. And in fact, we can do slightly better. So we can split the pullback of the VHS. So I'm going to use this notation V sub c. So this is the pullback of the VHS to the universal curve. This will split into, again, a sort of relative fixed part plus a non-fixed part, where this is the relative fixed part. Okay, meaning this is not globally fixed, but it's fixed on every fiber, on every curve there. Right, so the point is that if I pull it back, then on each of these curves I have a fixed part. So if I push it down by this map, the push for it will be non-trivial because of the sections on each fiber. And then I can pull it back and look at the adjunction map between them. And then because VHS is semi-simple, that thing splits. And so I split off this part that's trivial on each fiber. And then, in fact, we can do slightly better. So this is on this universal family, but in fact, you can get down to a finite covering of Z. So in fact, we can go to a finite covering that I'll call P from Z to B. And so this is by some kind of Stein factorization. So for that, I noticed that this universal curve is not proper. But if I look at the part of the universal curve that lives over B0, so that where I keep looking at only the part of this that really maps into B0, over that part, the map G is proper. Because, again, as long as my curves keep meeting B0, they can never break up into parts, right? They stay in this moduli space. The only sort of degenerations that could happen is curves that degenerate and move entirely into the boundary divisor. So by minimal degree, the minimal degree condition says that C is proper, G is proper over M0. And so then I can do a kind of Stein factorization. Okay, so what we can do is you Stein factor the proper part over B0, and then you extend it to a finite covering. So what you end up getting is you get a map to some Z with connected fibers, and then a finite map to B, where Z is normal, P is finite, and S has connected fibers. Okay, and P is actually étale over B0. So it's the unique extension of that étale cover to a finite map. I know. In this case, there's no. Okay, and the decomposition of the VHS that happens on the universal curve, from the fact that I have fixed parts on each curve, that actually drops down to Z, because the map S has connected fibers, right? So the decomposition descends to Z because S has connected fibers. Right? I mean, you think I'm decomposing a local system or a representation of pi1, but the local system is pulled back from B0. And so this map, on this map with connected fibers, the map on fundamental groups is surjective. And so if I have splitting upstairs, then it induces a splitting downstairs. Okay, and so then what I actually get is this decomposition of my VHS on Z into, again, a sort of something like a relative fixed part plus some non-fixed part. Okay, and so that's, I mean, that looks pretty close to where we want to go, because now I really want a decomposition on B in order to contradict Voisin's theorem. I don't get that, but I get a decomposition at least on this finite covering. So this is a non-trivial decomposition on a finite covering of B. Okay. Right. So there's yes. And so then maybe I should say how to. So the fourth step is to actually descend it and then to contradict Voisin's theorem. And so what we do there is we have to argue that in fact this finite cover isn't there, that is actually equal to B. But this is really the tricky part of the proof. So I mean here we got a lot of inspiration from Hwang's original paper. I mean we had an argument and it was wrong, and we had another argument and it was wrong, and each time we sort of try to fix it by going back to Hwang's paper and understanding better what he was doing. And so roughly the way the argument goes is like this. So what we show is that for a general curve, C, this cover is unramified over all points of C of the image curve. Okay, so I mean it's sort of by construction it's an étale cover where the curve meets, where the curve lies in B0, but we show that even at the points where the curve meets the boundary, this thing is still unramified completely. So in other words, what it means is that the pre-image under this covering, the pre-image of the curve really is a disjoint union of copies of. Okay? And then I claim that actually does the job. And so the reason is the following. So if you think about how this actually looks like, so here's our B, then there's some kind of boundary divisor, I don't know. I'm just going to draw it like this maybe. It's not really normal crossings, but this is the discriminant, right? And so what actually happens is that the Picard number of B is equal to 1, right? And so all of the components of this divisor are actually ample, right? And so therefore, our general curve, it really has to meet every one of these components. So if I map my general curve in, it has to really hit all the boundary divisors somewhere. Okay, and so if I know that this covering is unramified at every point of the general curve, then I get that it's unramified at the general point of each component of this discriminant divisor. Right? So this says that G of C meets all components of D, and therefore pi is unramified in codimension 1. Because I get a general point of every component of D. And then by purity of the branch locus, this means that P is actually étale. Right? But then B is simply connected. So since pi1 of B is trivial, we get that B is equal to C, or Z is equal to B. Okay, and so then our decomposition it actually really happens on B0, and then we contradict Voisin's theorem. So this says that V splits on B0, and that contradicts Voisin. Yeah. So that's the. Yes. Yeah, so P is unramified outside of D, yes. Right? Now, if the curve hits D at this point, I'm saying that if I look at the entire pre-image of this point in the covering, it's actually, over this point, it's a disjoint unions of just copies of the curve. So it means that at that point, there can be no ramification, because if there was a ramification, I would have a place where the thing is multiple to 1, and then I would have too few pre-images. Right? That's the argument.
Here you use you only use this condition that the Picard number is 1. This is the only thing.
This is the only place where you use the Picard number. That's right. That's right. So here in this sort of part, these kinds of things you can try to show more generally, but the conclusion that the thing is Pn, that has to use the Picard number 1, and that comes in at this stage. So, you know, if you try to do the same kind of thing in this S cross S maps to P1 cross P1 example, this is kind of where it goes wrong at that point. This is why P1 cross P1 is not P2. Yeah. Any other questions? Right, OK. I guess I will not show this Hodge theory argument. So maybe I'll just say that, so this argument is really relatively tricky, but so we really had many iterations of trying to weed out the errors in this argument. And it was actually the same with the paper by Lee and Tosati. So we had some back and forth where they said, like, hey, there's the stupid error in your paper. And we said, hey, there's the stupid error in your paper. And in the end, I think we found an errorless proof. But it's a little too complicated to describe it nicely in a talk. So yeah, so I think I'll just stop here. So thank you.